All right. So welcome everybody. And we're kicking off the second meeting of our technical working group this week. I have to make Adam Shear makes his apologies. He and his wife are at this very moment or very soon going to have their first child. So we send our best wishes and congratulations their way. And you're stuck with me instead. So I'm really happy to dig into this. The OpenEEmeter is a project that is near and dear to my heart, as well as Caltrack. My name is Phil. I've been at Recurve for a number of years, and was one of the original committers to the OpenEEmeter project. So we'll kick it off here. Let me give you a brief overview of what we'll be doing today. Let's go to the next slide here. So first, there was an item we didn't get to last time, which is logistics. I'm sure you're eager to know exactly how to contribute, how to participate in this process, and certainly attendance at these working groups is one of those primary methods, but I'll give you a little bit of a deeper dive. We didn't get to do that last time. And then we'll do the fun stuff, which is actually improving Caltrack. For much of that, I'll be turning the presentation over to Travis Sykes, who's here as our, guiding us through the analysis and huge technical resource on this in this effort, dedicating time to improving this and to fix some of the issues that we've seen. At that point and near the end, we'll leave some time for discussion. We'll also have a little bit of an opportunity to raise your hand and say, I want to help. We're getting a project started, getting going here, and I'll let Ethan talk through that right at the end. But let's get going now. And if you were here on the last call, you know that you can put a question in the chat or in the QA section. You can also just unmute and speak if you'd like, and that worked pretty well last time. So please jump in at any point if there's something you'd like to discuss. And I may say, hey, well, let's leave it for the discussion at the end, or I may say, let's talk about that now. That makes a lot of sense. So if there aren't any questions or early comments, in fact, I'll leave a moment if there are any comments or questions right now, and then we'll jump in. All right. So either you're still thinking about it, or you don't have any questions. So we'll move on here. First of all, some logistics. What better way to start than to look at the mission and scope of this LF Energy project. You can see that, some of the key text here. So I won't read it all out, but I will call out something that I'm not sure that we appropriately, well, we had a busy agenda last time, and so now I'll mention it, which is essentially that we're combining the open source engine and the methods all into one here. These both fall under the same charter in the OpenEEmeter. Previously, we had kind of a distinction between the methods and the codes in terms of how they were managed under two different charters. And now we're making a very kind of no-nonsense change, 2 words, and incorporating these all under the same umbrella. And our hope there is that this will allow these projects to be closer linked. They are linked at the hip already. And it's worth briefly sort of mentioning that, the purpose of this project is to build and maintain not only the code, but also the methods. And we're here, sort of the primary objective of making sure that, these building energy models are production ready, that we can use them as resources in markets, and that everyone who relies on them understands how they work and trusts them. And that is certainly that's a high bar And we hold ourselves to that high bar, and so we're here trying to figure this all out. Now, just a brief, to make this really concrete, we have the CalTrack methods, we have the code, and these are all now falling under the same charter. And of course, the community builds both of these. And you're the community, and there are others who have also contributed to this. That includes CalTrack, it includes OpenEEmeter, EEweather, we'll spend a little bit of time on today, and GridMeter. Let me barrel on here, and then I'll leave a little bit of time for questions at the end of this logistics section before we get into the fun stuff. Part of the charter is, are these principles for how we operate, and top at the list of things that we want to make sure is always true is that we are testing and that we are coming up with solutions that have a foundation in solid statistics, and in solid software development practices. That's really foundational to the way that we're trying to approach this here. And so a lot of our focus today and in future sessions, and as we go to make actual line by line changes to the methods and to the code, we're backing those with the evidence that these are improvements. And the threshold for improvement and for to enter a change into the OpenEEmeter or into CalTrack is that it is an overall improvement in the health of the project overall. Sometimes we do make changes that aren't perfect, that are trying to balance a lot of different things. And we'll get into that later, but it's really important that we have an explicit tie to specific changes, and we also don't make these changes willy-nilly. We maintain this version so that at any point we can go back and see what the version was earlier. We can lock versions to it in the context of programs. In just a moment here, we'll dive into kind of the process that we'll be using and enforcing or encouraging everyone to use when we make specific changes. So a couple of things, and I gave a little bit of a walkthrough on GitHub last time, so hopefully you saw that, and if not, the recording is available to you. So let me focus on this box here. I don't know if you can see my cursor. I think you can.
Hey, Phil?
Yes.
Sorry for before we get too technical. I just had more of a higher level question.
Please.
Matt Golden was mentioning California ISO flex meter methods. Just real briefly, if it's a brief question, if it's not, we can defer it to later. How does that relate to the OpenEEmeter CalTrack stuff? Because it wasn't real clear to me.
Yes, good question. We'll think of these as a suite of methods and code, and so if we're looking at specifically at demand response, that might fall under, and there are different names for them, but DR meter I think is a name there that we're proposing for something where we're looking at a short-term impact rather than a long-term baseline. So this is, over the course of a day or a few hours. How can we use a CalTrack method, and model to model that? And yes, that absolutely falls under this umbrella. And in fact, is one of the things that we have scheduled for this particular round. So,
gotcha. So flex meter is just a different phrase, different branding for some of those.
Sure. Yeah.
Yeah, sorry, this is Carmen. There are some semantic webs to navigate here. And one of the reasons why we wanted to put this project together, and it will at some point get a name change. So start noodling on what that might look like. But FlexMeter, in the context of that CAISO study, was representing the combination of Caltrack and what we called GridMeter, which is the comparison group analysis, and then applied in a demand response sort of context. So you don't see FlexMeter on this page because it may or may not have standing as an open source thing, or it might end up being kind of a different combination of names. But for now, we're trying to just lay out the fact that these things are related. The differences between them are really the functionality and the context of where they've been used so far. So, but we also are self-aware enough to say that our naming conventions have gotten a little screwy. So we need to do some cleanup on that front.
Okay, cool, thanks.
Thanks for jumping in, Will, and Carmen on that. Any other related questions or comments? If not, we'll jump back in here. I wanted to just highlight how the mechanics, and this is really getting into the details here, so I'll try and keep it brief. But the mechanics of how we make a change are important, because we have to respect the current methods, and we also have to make important and necessary changes, and balancing those is important. So there are 4 key things to call out in the change, and we're holding ourselves to a high bar here. I think you'll see that this is a high bar. We start with a problem statement, some issue we want to solve. We have a hypothesis for improving or fixing that change or fixing that problem or issue. We back it with analytical evidence that it is an improvement, and also that it doesn't negatively impact other parts that, some changes may have cascading effects. And then finally, and very importantly, we tie that to a discrete change to the language of the method. That might be striking a sentence and replacing it with something new. It might be adding a paragraph. It might be adding a section. But that's an important way that we keep this concrete. As we go through this process, you'll see this analytical process that Travis, I will give him as much time as I can just a moment, because that's really where we want to be focusing. But ultimately, the technical steering committee, which we introduced last time, will be reviewing these and approving them, providing rationale for these changes if we make them or not. Any questions about this? Excellent, thank you. So I'm gonna, these slides should be available to you. This is a page with a lot of links in case you need to go find something. So I won't talk too much about it, except to say, if you're having trouble finding anything, this should have it listed. Now for the fun part. So we are really trying to fix, we're trying to understand so that we can fix the sources of bias in the Caltrack daily model, as one of many areas of focus for this round of Caltrack updates. That's this one at the top here, but there are others. Can we make computational efficiency gains? Can we fix some small bugs? Can we improve demand response and kind of combine some of the things that Carmen and Will were talking about under the umbrella of Caltrack and the OpenEEmeter? And we absolutely can. And so these are our initial goals, but we will be moving, I hope, in fairly short order to the rest of these as well. Jumping into the details, and I will be light on the details, and Travis will be heavy on the details in a few minutes here. But this is a reminder from last time. What we're doing here is we're we've identified a few sources of bias where a model will systematically over a whole population or even for a particular building underpredict or overpredict particular seasonal loads or weekend loads, or maybe isn't taking into account thermal lag. A chart we spent a lot of time on last time that I will only briefly review here. But again, what you're looking at are kind of over a bunch of different models, averages of where the model is over or under predicting, and in comparison to the observed load or the load that's measured directly at the meter. And if you're going to take one thing away from this chart, it's just to remind you, we have summer in green, shoulder season in red, and winter in blue, and we're looking at gas consumption. And where you're seeing a peak, you're seeing over prediction. When you're seeing a dip, you're seeing under prediction relative to the balance point. And clearly there is a difference season by season. And we see that as evidence of what we might call underfitting. There may not be enough variables in the model to fully explain what's happening, particularly if there are differences in how space heating is related to outside temperatures as measured by a nearby weather station in winter rather than summer, and vice versa. And this is an important point and one that we'll be spending some time on today. So let me pause here and see if there's any clarifications from Travis or any questions from the group.
So one thing I'd point out is that the reason why we have to basically recenter all of this data around the heating balance point is because every single meter is going to have its own model, and so therefore if we were to simply look at temperature, that would kind of smear this entire plot out. So what we're trying to do here is basically to focus in on the change from the temperature independent to the heating degree days. And this helps us understand exactly where the error is happening. And from then dividing this up by the various seasons, we're able to see that, for example, in the summer, you see a rather high overprediction. And then in the winter, you see an underprediction. So basically, because there's not enough parameters in the model, it's being forced to split the difference between summer and winter, and then the shoulder is somewhere in the middle. So that's what I would add.
Excellent, thank you. Finally, one more chart, and then I'll hand it back over to Travis. Wanted to show you the seasonal, like maybe two charts. This is what you're looking at, are a count of buildings where you're seeing an overall error. So this histogram is showing you that in the winter, this error there's a lot of red there, not a lot of blue. So clearly there's a bias, and you're seeing the opposite effect during the summer. It's pretty noticeable. There are some buildings, of course, where it actually goes in the other direction, but overall, you're seeing a significant bias during different seasons. So this is just another slice of the data. It's the same data, looking at it in a different way. With that, I will pass it over to Travis.
All right. Do you want me to share screen, or do you want to click for me?
I would be happy to click for you either way. Let me know if I'm getting in the way.
Let's do that. All right. So basically, when we're looking at how to fix these models, we need to look at a lot of things. We need to obviously lower the model bias that we're seeing, which is kind of combined with the uncertainty. But something else is that we have to can factor in here is that we want our model to be predictive. We don't want to go into the, now that we're adding more variables in, we don't want to go into the realm of overfitting. And so then we have to kind of balance this idea of simplicity versus complexity. Basically, we want the model to be as simple as possible, but as complex as it needs to be to describe what we're seeing. The next thing that we need to worry about is interpretability. And when I say that, what I'm primarily referring to is, can I go to a layman and with relatively small amount of time explain to them how our model is functioning? Maybe not go into all of the details, but as at a basic level, have them understand what's going on. This is also really helpful for the professionals to be able to basically disaggregate heating load and cooling load, is if we're able to preserve having cooling degree days and balance points. And then lastly, everything that I've mentioned here is talking about adding computation. It's all kind of pointless if it takes an hour to run a single meter. That's going to be completely untenable if you're wanting to run this on 1 million meters. So we have to make sure that however complex we make this, it still runs fast. We can go to the next slide.
Coming right up here, just a moment. There we go.
So now I'm going to switch into talking about kind of where we're currently at as far as ideas, as well as to show some preliminary work. So what I didn't get to last time, but was in the slideshow, was talking about ordinary least squares. So with ordinary least squares, you might remember from last time I was showing these kind of pseudo plots pretty regularly, where on the y-axis I'm showing energy usage and on the x-axis temperature. Now here I'm showing winter as the purple dots, shoulder months as in fall and spring being combined together into the green dots, and summer as blue. Now with ordinary least squares, one potential problem which is how things currently run, but one potential problem with that is that it is highly influenced by outliers. So for example, if let's say this household goes on vacation during the summer, and in fact, during the summer, whenever they are on vacation, they just shut off their power. So their power is going to go to near zero. And so then whenever we do an ordinary least squares regression fit to that, the entire model is going to be pulled down. Greg, you have a question?
Greg, if you're speaking, we can't hear you.
We are not able to hear you.
Can you hear me now?
Yes.
Sorry about that. Yeah, I didn't want to get you off track too much, but this is a good point that I didn't get a chance to bring up last time. So with least squares, if we're measuring things like therms, which are a pretty big unit of energy on a daily basis, you will get a lot of sort of zero reads on a daily basis, like in the summer when there's no heating load, for instance, if it's just cooking or something like that. So we see higher error for, it'll go between like 1 and 0 therms every other day kind of thing. And that's fairly common. Is that something you guys have the capacity to deal with, or something you've identified? It really depends on, what people are using gas for. And again, this is mostly in the summer, but definitely have seen higher error rates, with that kind of case. Does that make sense?
It's going to depend entirely on what the rest of the data is looking like. Like if those 1 or 2 therms in the summer are outside of the norm, and otherwise they use a lot or they use none, or if they use a lot, then those would be seen as outliers. For example, in this plot here. However, if instead that becomes more of the norm, then what the model would predict would basically split through all of those. And so the model would predict something like 1.5.
Right. So but the total error, since, they're using a half a therm a day, and that's what the prediction is, the error is still the sum of the squares the difference between the points and that model, right? So there's still error, even though, is my question making sense? Am I?
If I'm understanding your question right, you're basically asking, are we going to be able to predict low usage? Am I following?
So this comes down to more of a measurement resolution issue, right? Like we don't typically see greater than or less than a therm of resolution, on a daily basis, right? We're not measuring like a tenth of a therm on a gas meter typically. So, it may look like they're not using any one day and then, they hit a therm the next, back and forth. So that is, perceived error, but it's really just a function of how good we are able to measure therms, not necessarily they're on vacation or whatever. Does that make a little more sense?
Yeah. So as far as resolution goes, there's really only so much that we can do. It's entirely based on the data. So the error is going to be, if it bounces between 1 and 2 every other day, the error is going to be 0.5. There's really nothing that we can do about that, because to be able to put in another variable to check whether or not there is one pattern on, let's say, even days and one pattern on odd days, like you can just continue to add more and more parameters like this. And we have to basically put the bar somewhere of like, well, we accept that there will be so much error so that the model is slightly simpler, but will explain a large number of buildings.
Okay, that's what I figured. Thanks for diving in on that.
And Ethan, you had a question?
Well, sorry, I had another meeting, so I just joined, but halfway through that question, but it's the one that's plagued us for years. And I've always assumed that it was a data prep issue, not a modeling issue to deal with it. I mean, essentially, we're undersampling the meter in that case. And so in order to reconcile it with days, we need to do some kind of a rolling average or some kind of a linear interpolation, right? I mean, that's effectively what we're looking at when we have every other day a single therm registered, is that actually what we have is half a therm per day is our best estimate. The only other way of dealing with it is go the other direction and put the degree days between each legitimate reading, right? So we have 2 days between the two of them, we've registered a therm of energy use. We don't know if it was 50-50 or 75-25, but we can calculate how many degree days happened over the 48-hour period between legitimate readings. So it's the same sort of thing you deal with if you had a accumulating register meter that went offline for several days and then came back online and told you, this is the sum total of my usage, but I lost all the intervals in between. That's effectively what we're dealing with here. Again, it's data prep. It's not another model parameter.
Yeah, data prep could be a way to handle this as well. Honestly, this is something that we will probably have to think about a bit more. So I'm going to just push that off to the side now. Keep it in mind. We'll add it on some things to think about. All right. So back to the ordinary least squares. The problem that you run into if you have these outliers, such as seen here at the bottom of this plot, is that it pulls the entire model low. And one thing that absolutely you must keep in mind with this model is the point of this model is not actually to have the lowest amount of error within this data. That is not the point of this. The entire point of this model is the counterfactual, which is to say, how well does it do in predicting future usage or what would be future usage? And so I would argue that, for example, in this case, these outliers should be thrown out, and that what you should instead shoot for would be to split through the summer just as you do through winter and shoulder, ignoring those points. If you can go to the next slide. Yes, Ken.
I'm sorry. I thought you said that these are potentially vacation. They're not outlier. I mean, they're outliers, but they're real. They can't be thrown out. Then we're overestimating.
They are very real, but they are abnormal usage. And there's no way to know that on these days in 1 year from now, that they are also going to be going on vacation. And so all we can do is say that we are going to capture the bulk of their behavior so that in the future, we have a best estimate for that meter's behavior.
If someone goes on vacation for 2 weeks each summer and we toss it out and then we do a weather normalized pre-post delta annualized, we've overestimated their savings by whatever percent potentially, because you're implying they're using their consumption is the same across the whole year, when in fact for 2 weeks they were just not using anything. So there's no savings those 2 weeks potentially. I mean, and if we're at the hourly level, we've got to sort of think the same way, I think, don't we?
I think Travis
this is really going to all come down to, oh, sorry.
Go ahead, Travis.
This is really all going to come down to what testing shows. Like, I agree that there are some instances where perhaps January 5th of every year, they do the same exact thing that is abnormal. And in which case, yeah, we should actually take that into consideration. But the flip side of that is we are looking at the daily model right now. So those 364 days are also going to be quite a bit more important than that 1 day. So if we go into doing the cross-validation as we plan to, which will allow us to sample, to test within sample, then we'll be able to see what is the better choice. Is it to do a adaptive robust loss function where we downweight outliers, or is it to use the ordinary least squares? That way we can elevate this discussion above whether or not we think that it's right or wrong, and reach the level of mathematically and statistically, is this the better thing to do?
So just one question then. So are we pulling them out for the purpose of validation, but that when we go back and apply these in the actual process of an evaluation, we would not throw them? Or are you saying that removing them as outliers would actually become, kind of part of the process?
So what I'm going to be proposing is not that we remove them, it is that we downweight them, which is different. I am also going to say that how the final model works, whether or not we use cross-validation within that, or if we basically use the cross-validation to show us what the best way of developing these models is unknown right now.
Okay. Move on.
Shay? No? Okay. All right, so the proposed solution is to instead move this towards an adaptive robust loss function. And so what I'm showing here is kind of well, not kind of, this is the state of the art as far as being able to do this with a machine learning intelligent methodology. So on the top left here, I'm showing the loss response on the y-axis and the standard deviations from the mean on the x-axis. So on this top plot, where 0 is, would be if your residual between the model and the observed value is a 0. And then 1 standard deviation from that, 2 standard deviations, and then on the reverse side of that. Now, the function that I'm using is able to replicate sum of squared errors, which is shown here in black, and that is when alpha is set equal to 2. It's also able to represent kind of a smoothed L1, and L1 is a general way to refer to just the residuals as they are. And then this goes all the way to a Welsh loss function, where when you look at these, what you're effectively saying is, okay, if it's one standard deviation away from the mean, then you would end up with a value of a sum of squared errors of about, let's say, 1.5. Whereas opposed if it was Welsh, then one standard deviation away would come up to about 2.5. Now, the reason why these are all offset is because you basically have to penalize these lower alphas where it downweights outliers more, because otherwise the function would immediately, what we will be optimizing here, by the way, is alpha. The function would immediately want to pick the smallest alpha because it's the best. Whereas if this has been penalized properly, which this has, this is based off of a Google research paper that has a lot of citations on it. If this has been penalized properly, then you will reach a balance point where you downweight outliers versus making sure that you include as many as possible, so you're closer to sum of squared errors. Now, once you've basically determined what that alpha is, you can then go down to the plot below. And this plot is showing how this is actually used. On the y-axis is the weights, and on the x-axis is, again, standard deviations from the mean. So if you pick sum of squared errors, this is these weights are being used in the function for a standard sum of squared errors system. So if the weights are set all equal to 1, then it is a sum of squared errors, whereas each one of these functions represents the functions that I showed up above and how those would kind of respond and downweight outliers. And what you end up with is something more like what I was discussing before, which is to say that the summer model then splits through the data, ignoring these vacation days that were unusual behavior. I seem to have missed some of the chat. I will assume that Phil and Armin are on top of it. So let's move on. Okay, so the all-important cross-validation. I went over this a little bit last week, but I'm going to do it all over again because I think that it is that important of a topic that everyone understands this. So for the cross-validation, we start here on the left with the solid gray bar, and that represents 100% of our data when we are developing this model in the baseline period. Now, when we're testing, what we can then do is we can break that bar apart into 30% of it being used for the final test validation, and 70% of it going into being used to make K-folds. So then we're going to focus in on that blue bar. And for the blue bar, that's then going to go into the cross-validation process, which is where we go. Basically, let's say that we want to have 10 different folds. Well, what we would do is within these folds, we would say that 10% of the data is being set aside for testing within that data set. And then 90% is what we're using to actually fit the model, fit the coefficients. That way we can look at that 10%. Now, this 10% is not, it is shown here for graphical purposes and simplicity only, but it is not the first month, the second month, the third month. We pull points from all throughout the year, but it's just 10% in total. Then we do that 10 times where none of these repeat. We pull different days for each of these different sets, as well as fitting models for each of these 10. From there, we're able to estimate what the error is by using these models and then looking at the test sets. Now, this is going to be very useful because this is basically telling us that we are able to predict what the answer should be based upon our test set. And then finally, when we pull all of that together, we then are able to look compared to that final 30%, and then we're able to see, well, was our estimation of our error accurate for what we actually see? So putting all of this together means that we are able to get important metrics about how predictive our model is based on error metrics, maybe R squared, just whatever kind of metrics that we want. We can move on. Now, in the implementation of this for our data, what we actually need to do is to do a stratified k-fold cross-validation. The reason why we need to stratify it is because the data within our distribution is not uniform, which means that if we're randomly pulling days out, then we may be underrepresenting weekday, weekend, or we might be overrepresenting winter. So instead, what we have to do is we have to bin by season, weekday, weekend, and then by temperature, so that we sample evenly throughout all of these various bins. And then from there, we know that we have a fold that is representative of the data set as a whole. And the primary benefit to this is that this will allow us to do within sample testing, so that we don't have to make the assumption of, is the set of data that we're working on from 2019, even though there was no intervention, we're going to just make the assumption that it's also going to act the same in 2020. So by only looking at 2019 and breaking up the data like this, we're able to basically test within the same year, and still be able to assess what the model accuracy and predictability is. This will also help us alleviate overfitting, because if you have too much overfitting, then your total error is going to drop, or not drop. It will raise, and the predictability or predictive capability of the model will decrease. And then finally, this will allow us to steer our hyperparameter selection, possibly in the final version of the model, but most definitely during development. Ethan, you have a question?
Yeah, a couple questions about how fine we want to slice some of this stuff. So if I'm doing my math roughly right, we've got about 250 days left in the test set. And so there's like 25 and the 10% for each of these cross-validation runs. So we're spreading that 25 days across. We've already got 8 bins by just doing season. Well, maybe only 6 bins if we combine our shoulder seasons. And then we've got temperature, right? So we've got like 3 to 4 temperature gradations we could get within each one of those bins. And I guess I'm just wondering, is it worth like sort of explicitly saying, now we're going to have like a low, medium, high day, like 1 summer weekday in the low, 1 in the high, and 1 in the medium bin for temperature? Like, is it worth explicitly binning the temperature versus having a little more diversity in there? That's your recommendation? And then the sub question to that is, do we want to explicitly do weekday, weekends? We got restaurants who, are shut down on Monday, Tuesday. Do we want to cluster days instead of explicitly doing weekend, weekday?
So Armin, I'm about to pass off to you. I will say that the percentage is right now kind of an unknown. Like, we don't know exactly how much we're going to break off for each of these. We just know that this is how we're going to be testing in general. Now, Armin has already done some work on developing our internal cross-validation process. So I'm going to pass off to him for more detailed answers.
So I was answering some question in the chat. I didn't get the exact question. Can you repeat the question, Travis or Ethan, please?
Yeah, just basically, it's like, where's the trade-off between the number of parameters that we use to bin as we're doing all this? Because we've got like multiple slices, right? We're saving some for our final test, and then we've got, the 90-10. So like, when you look at that sort of 10%, whatever that number actually is, there's like 25 days. And so if you're explicitly binning by season, weekday, weekend, temperature, like how many different, like, we start to get to like 1 day in each bin, right? Where's the trade-off?
So each one of these columns that you see, that's the whole data set. So that
Right.
10% means, like, for example, if we have 365 days, that percent is like roughly 36 days. And if
I thought
you're
you
binning,
withheld
I thought you withheld the 30% for the final test.
Yes, that makes sense. You're right. So that would be like
25.
300 days.
Yeah. Sure.
Oh, you mean over
200
the, okay, so if we're doing for the test, that 30%, all of that would be for the test. This side 1090 is just for the cross validation to make sure which error is the best for our actual training set. So after that, that 30% would be actually, the whole thing would be our test set on top of the best model, on top of these training set.
Right. Yeah, I'm just thinking about the 10% of the 70%. It's pretty small. If we're bidding that one as well, which I assume we are. But why don't you take us through what you've been working on it specifically, and then
so basically that 10% would be 30 something, and like in the worst case scenario, as you mentioned, we have seasonality and the weekend weekday. So we have we divided that 10% to 6 parts. So that 30 would be 5 in each, and that 5 is being sampled from the same filters that we have for the 90%. So we don't that much bin from that 10%. We bin with that 90%, and then we just select that.
So the 5 aren't being explicitly binned by temperature?
That 5 would be inside of one of those categories of those 6 in the worst case. Yes. So that 5 would be binned from that, from each of those categories. So it has been binned from the beginning, but in the test set, we just select from them. So we don't bin again inside of the test case.
Okay, well, let's see how it works out.
And we can always alter those percentages to fit how we need. Once we have them set, though, we will keep them as that.
For sure.
Still a little bit of work to be done there. We can move on. All right. So okay, so in general, what we're shooting for is to minimize overfitting. As I mentioned, the cross-validation is going to give us some information about if we are overfitting or not, but we also need to be able to determine that while we're fitting our models. And in general, the way that we're going to be approaching this is to minimize the error, but also to penalize by the number of coefficients. And I'll be going into a little bit more detail of this later on. So we can move on. And we can skip past that. We're switching to talking now about actual data, not just ideas that are being put forward, but are actually implemented. So this is an example of the adaptive loss function in action. And here I'm showing usage in kilowatt hours. On the y-axis, x-axis is the mean temperature in Fahrenheit of a given day. So here, what you see in the black line is Caltrack 2.0, and the orange line is the current changes that I've made. This is basically showing a real life example of what I was talking about earlier, which is if you have a few points that are quite low, it will bias your entire model downward. So now instead of being wrong for 2 days, you are off for the entire season. So we have to balance how accurate we want to be. Like we can make it so that we are as accurate as possible in the baseline period, then we do sum of squared errors, great, everything's fine. Or we try to make sure that the model is predictive, in which case we want that to go through the bulk of the data while downweighting these outliers. So for example, here, I see the orange line as basically splitting through the bulk of the data with the exception of the bottom 5 points or so. Again, this is like a by eye test right now. we're in the process of implementing these cross-validation schemes and being able to test the error and accuracy of these models. So we can move on. Another thing that I don't know if I mentioned last week, but it is something that I've put some work into, is changing the functional form of our models. Previously, the functional form of the models were all linear, piecewise linear functions. There are some cases where I would argue that what you see is more of a gradual onset of heating or cooling. Right now, we're looking at electrical data or electric data, so this does have cooling as well as heating. And again, the black model here is the original Caltrac 2.0, and the orange model are the new changes. So what I've done is basically added in an option where it has an exponential decaying term, so that you can have a smooth transition from the temperature independent region to the cooling degree days. And then that decay will decay off into the same linear slope that we use in the current methodology. The current setup of this is that if the smoothing is selected, it will basically add 2 coefficients to the functional form, and it will do that on both sides, both for heating and cooling. Or if it decides there is no heating, then obviously it's only 1 more. This would be an example of where I would say that it is a reasonable assumption that the curve be a little bit more smooth than the just jagged connection of the piecewise linear. Whereas if you look at the junction, the balance point, it's a little bit low compared to the rest of the points on the Caltrac 2.0. Whereas for the orange line, it splits through the data a bit nicer. Ultimately, the entire purpose of all of this is to be able to basically just reduce some uncertainty. This is unlikely to change much in terms of bias. So we can move on. Last week, I had talked about splitting things up by weekday, weekend. This is an example of that functioning. So the top points here are weekdays. The colors represent the seasons. Though there's no break-in seasons, it's all the same model. So it's basically just 1 linear model in this case for the weekdays, and 1 linear model in case of the weekdays. And this is all functioning such that the model, I don't actually tell it to make a split between weekday or weekend. It chooses to either include a weekday weekend split or not, based upon our model selection criterion. We can move on to another example of a weekday weekend bias, where this one has a little bit more complexity to the weekdays. It has some heating days as well as some cooling days, not much temperature independent region. And then on the weekends, it's more or less a flat line of constant usage. Without being able to split weekdays and weekends or to have a unique variable for this, what you would get would be something more like the black line, both shown in the prior example as well as this one, where it's basically just trying to split the difference. And what you end up with is that it doesn't capture anything well. We can move on. Now, the same thing can be done for seasonal bias. Now, this is a bit of an extreme example. One of the more bizarre meters that I've seen as far as seasonal bias goes. But what we see here is that basically winter acts entirely different from the shoulder and the summer. A lot of 0 data points, but there's also some pseudo heating cooling days and heating days. Now, what we would basically say is that every winter would follow this model, whereas every shoulder or summer day would follow the models up above. Both of these are have the exponential smoothing in them. Again, I did not pick this. The algorithm picks this. But this is to show that when these things should be split apart, the algorithm does a reasonable job of estimating when that should happen. And we can move on. So I mentioned the model selection criterion, which is how I have basically taught this model to pick between which selection it should pick as far as model complexity, as well as the number of splits. These models are all, these model criterion selections are all based on the log likelihood at the moment, where the only key thing to really take note of in this top equation is that we care about the loss function, which is the combined error. The loss, you could read that as the sum of squared errors in the case of where you are doing sum of squared errors. Now, the penalization that I mentioned previously is shown on this second equation. It is the term K, which again has some correction to it afterwards. This one specifically is the sample adjusted Bayesian information criterion. You can find that in the literature if you would like to search for it. So basically, what we see here is that ultimately the two driving factors within this are the loss function, or sorry, not the loss. It is the loss, which is the combined error, which goes into the log likelihood, and then you add to that some function of the number of predictors and some split penalty. So all of this together means that if you get a better log likelihood, aka smaller error, then that can be offset by how many predictors you need to include to get that, so that there's a balance between complexity of the model and accuracy of the model. One note here is that while the number of predictors is quite easy, the split penalty is a optimized term that we're kind of working on figuring out what that penalty should be. But so far, what we've wound up with is picking rather good splits. We can move on. And this now gets us to the most complex example, which is where we have both seasonal and weekend bias. Here, summer is basically acting more or less entirely separate from winter and shoulder days. I guess I should first mention here that the weekend acts virtually the same for every single season, and it's more or less, let's see, it's more or less flat, but it's that is based upon the scale that we're looking at. So it actually is a linear model. I'm not going to explain that. It's a cooling degree day model. The winter and the shoulder show a very different behavior together than the summer weekdays. And then basically the difficulty is that we have to take into consideration all of the various permutations of splits, whether that be weekday, weekend for winter, or we want to combine everything together for shoulder. And it ends up that you have roughly 60 various combinations that you need to take into consideration. This gets back to our quest for computational efficiency, which clearly this at first glance is not. Yes, it does consider the combination of all seasons as well as keeping the weekends and weekdays together. So every combination that you can think of weekday, weekend, and the 3 seasons are considered.
So there could be a scenario where like winter and shoulder is one bucket, summer is another bucket?
This example right here. The winter and shoulder are one single model together for the weekdays, and summer weekdays is its own separate model.
Oh, okay.
Another thing that I am currently struggling with is do we have enough functional form? Because this example right here, you could more or less fit this with a sigmoid, where it would instead of just stopping at the winter and shoulder, you would have a smooth transition into summer. But then we get into interpretability and are we able to preserve balance days? Like all of these splits that I'm describing to you, we're still able to preserve our balance points. It's just that the balance points are going to be relative to the season or to weekday. But you can still extract like what is the cooling load, what is the heating load. So we can move on. And then we move on to some stuff that we hope to talk about next time. And that is computational efficiency. I do have some ideas and some preliminary work into like basically what I just described was we need to run the model 60 times and fit 60 different models to pick which is the best one. That's not so great for computational efficiency. I've already got some ideas on how to fix that, as well as some preliminary work there. I also hope that by next time that I will have gotten to dive into the thermal lag. I'm kind of calling it thermal shift now because Steve's comment last time about having the temperature lead the indoor energy usage, I think is entirely valid and it's a good idea. And so that's no longer really lag, it's more of a shift. Hopefully, we will also be able to talk about our multiple linear regression model, as opposed to everything that I've talked about so far, as well as an exploratory neural net that we've been working on. Additionally, if anybody wants to like dig in and start testing these things, like submit some stuff to the GitHub, this does not have to be just us showing you what we're working on. If you have work, we can next week we can showcase it and we can have your own presentation. So just let us know. Yes, Ethan.
Is multiple linear regression, are you talking about adding more breakpoints, essentially?
No. So the multiple linear regression model is would be entirely for prediction. So the way that we're thinking about this right now is that if you want to be able to preserve the ability to split into heating load, cooling load, base load, and so forth, that you would have to use something like what I've been working on. But we don't really want to we don't want to limit the predictive capability of a model based upon these additional requirements. So instead, we're saying, okay, well, what if we have two models, one where you can do that and one where the sole purpose of it is to give as great of a answer in the reporting period as possible.
Okay, so two models for different purposes.
Yes. Yes, Glenn.
Hi, thanks, Travis. Are you going to be reviewing the time of week and temperature model for the hourly methods?
I am.
Okay, just checking. That's the one I'm more familiar with, and I kind of like that one since it we have all this hourly temperature data, and these daily methods just uses the average temperature for that day, and it seems like that would be a huge source of kind of hiding the errors we may be getting, since, for example, San Francisco, where I live, the temperature doesn't really change that much all day long. Sometimes it'll stay right around 52 degrees, but you go the other side of the bay and into the getting in over the mountains there, it'll be freezing at night and it'll be 75 degrees and during the day at the peaks. So all that granular data, it seems like we'd want to use that. But anyway, I digress. I just wanted to make that comment.
I actually entirely agree with you. And what I intend to do with my thermal lag, thermal shift work is to do this based upon the hourly temperature data, so that wherever that shift is, as far as an average in the past or in the future, or how many days and so forth, we do that by the hour, not by the day.
Thank you.
Mhm. All right. Yep. Yes, Ken.
Yeah, so you mentioned interpretability, and I guess I wanted to kind of just go back to the beginnings of this and remember that, back in the 80s when the Princeton scoring method was developed by Meg Fells, et cetera, with, degree day set points, and there's a whole kind of engineering theoretical model that heating starts. This is the temperature, outdoor temperature at which heating starts, and so forth. Clearly, with a monthly model, you don't have the kind of the daily subtlety that you're dealing with here in your shoulder, in these kind of shoulder periods, in terms of this bias. Something that was recognized even back then, though it wasn't all that obvious to see in the models, is that these models consistently underestimate water heating load, and it gets conflated with heating load, essentially. We use a lot more hot water in the winter, and various efforts have been made at times to actually go and test that and try to quantify that, and it's a function of the number of occupants and so forth. And it seems to me that the nonlinearities you're seeing around, the degree day, sort of the base point you're using for your degree day is, it may well be that I think hot water usage increases earlier than the furnace turns on, and so you've got kind of two different degree day correlated processes going on that are driving overall consumption. And back again, once we were dealing with monthly data, there was no way that was going to get pulled out. And I've tried to think about how one could specify a model that would actually attempt to deal with that. And obviously a jointed, even just a second joint in the smoothing you're doing sort of implicitly does it, I think. But it's worth keeping in mind, because it's well established that the water heating is getting conflated with space heating, and there are implications for that now that we have this more granular data. And more generally, I guess where this point comes from is that this kind of modeling, one of the nice things about it, at least for me, has always been that it actually does have a kind of an engineering basis, right? We all live in houses. We know what kind of things are behind this consumption, and it is there is the possibility that an engineering perspective, as opposed to a kind of a more just sort of statistical method approach, could be more informative here. So I guess I would just keep that in mind. And the water heater is sort of the first example of that comes to mind. I think when we get into hourly data, there are similar kind of some other things like that we can think about.
Well, you will be happy to know that my PhD is in mechanical engineering, and that I come from a world of heat transfer and thermodynamics. So whenever I'm thinking about these models, I'm thinking of them in terms of being a statistical model. However, I can try to inform it with mechanical engineering principles whenever possible.
Great.
Glenn, did you have another question, or is that just your hand still up?
Oh, no, sorry. I didn't know I had to unraise it, I guess. Yeah, sorry, thank you.
No problem. All right, so we can move on to the next slide. And I'll pass it off to Ethan.
Hey, thanks. I am not going to throw up slides because this stuff is pretty simple. I'm just going to go through a short discussion here. And we can talk about a couple of the main issues. I think the context here is that there's some opportunities to make some improvements to EE weather. And so the task I think that we want to tackle now is like figure out what are the priority fixes that are worth spending our time on, and also identify the group of participants who are interested in putting some time and effort into this, at least mind share, but maybe also like fingers on keyboards and doing some coding. So the list that I've been carrying around with me for EE weather improvements, so this is sort of the first thing probably is brainstorming if there's other pieces that folks are interested in. Number one, data caching. Takes a lot of time and it causes problems sometimes if people don't have consistent access to the data source. I think there's a similar piece of that, which is like NREL has moved to a different system for the TMY3 data. So accessing that and figuring out how to deal with the gridded TMY3. So that's all sort of in that category of like data access and data caching and what's the best way to manage the data. I'll expand that a little bit more and put a second topic on non-US addresses. So there is some non-US data in the ground surface data set that we've been using, but like zip codes don't work. And anyway, there's like some issues once you get outside the US. So I know that there's more folks now getting involved in this who are outside the US. I've had a project come talk to me about Canada and like, doesn't seem like it'd be that hard, but zip codes, they're US. So that's sort of the next extension on data access. And then the really quantitative model oriented item that I've had on my list for a long time, this is probably the more fun one versus the more mechanical ones that I just listed, is about climate change and TMY3 as a good predictor of future temperatures, right? And so there's two different methods that I've come across that we could explore, and maybe others have had ideas. So one is that there's like actual climate models for different geographic areas of what we expect the like temperature norms to be in coming years, right? So like actual planetary models that people have built that say in San Francisco, here's how much hotter, here's how much colder it's going to get in different months, things like that, right? So they've done these predictions for different geographic areas for different years in the future. There's like monthly norms and things like that, but they don't have hourly models, right? So there's one path that's like, okay, let's take these like physics-based planetary models that give us predictions about how the temperature norms are going to change. Let's take the hourly dynamics from past data that we've seen, and let's try to like shift that in some intelligent way to be able to match these forecasts about the future. Doesn't really tell us whether the amount of dynamics that we're used to seeing are going to stick with us in the future, but maybe we can try to inform that. So that's all, that's sort of one path, is like take some past patterns and some future forecasts. The other one is more of the statistical approach to it, which is just like, let's take the last 10 years and use that as a forecast set. Instead of taking a typical, right? We don't actually need to see 1 year, right? We just want to see like, what are the norms? So you could literally take a CalTrack model today from your counterfactual and say, let's just see what it would have done with the weather from the last 10 years. And then you could apply some weighting to that, or some forecasting to that, and say, how often are we going to have peaks? How high are the peaks going to be? What are the annual averages going to be? Things like that, using those past 10 years. So that's a little bit more simplistic. Doesn't depend on these like planetary models. But those are the two different approaches that I've thought of. There are probably other ideas out there from folks who've been thinking about this. I do know that like University of Oregon or some academic group in Oregon is working on this. I've been told for a couple of years that any day now we're going to make an introduction. I'm going to get to hear what they're working on. So we should bring them into the conversation too, probably, if we're actually going to like work on code. But those are the topic areas that I think are appropriate to work on with EE weather, is like better data management, make it easier and more robust, and better geographic scope to get good data, and then deal with TMY3, right? A combination of gridded TMY3 and climate change aware forecasting, particularly around peaks, right? The folks who are concerned with grid peak forecasts are looking at last year's Northwest numbers, these like 110-degree days, and then looking at the peaks that we forecast with TMY3 and not buying it. So those are the ideas we're interested in. Other folks either have other ideas about things that could be improved about EE weather, other methods that we might use to solve the problems I've identified, and then in particular, volunteers to put time, data, money. We'll take money. If you want to throw money at us, we'll find people to work on it. That is a valid option. So questions, volunteers?
I just have a quick question about the solar data. Does anybody know any available solar data that we can use for the PV generation prediction? Because I searched for almost like 2 weeks. I couldn't find any available free data set that we can get the data for 2020 as well, not just 2020 and before. And yeah.
That's a good question. So I don't know of an easy answer to that. I do have a really good contact inside one of the largest solar monitoring companies in the world. And so they've got actually like really good calibrated pyranometers all over the place, but it's all like customer data. And so we'd have to be able to convince them that there's a way to anonymize it appropriately and somehow either compensate them for being able to deliver it, or convince them that it's worthwhile, or convince DOE to compensate them to kick it out or something like that. One other option.
Does NREL not have those data you're looking for?
NREL has data till 2020, and they will update it for 2021 in a couple of months, but there's no way we can have data for 2022 anytime soon. And that's a problem for our customer, because we need to like sometimes report it for monthly basis.
I know that there's I might be saying things I don't fully understand, but there's like a threads server we looked into at one time, and like PVlib library, some HRR data or something. Did you look into that stuff?
Yeah, I searched it. They deprecated all of those forecasting methods that they have, all of them. So that was the first thing I checked after the meeting that we had.
Yeah, that makes sense.
Yeah. Right now we are using Solcast data, which we have to pay for it, but we did it for just research purposes.
Okay, good.
Another question?
Hello? Can you hear me okay?
We can. So now we can hear you.
I hear somebody quietly speaking. If you can speak into your microphone.
Yeah, I guess I'm trying to say I'm from a building performance analytics background. This is my first meeting, I guess, attending this EE OpenEEmeter. The weather data we have, there's a bunch of study in the building performance analysis community around future weather files. There's like people trying to analyze what's the impact of climate change in the planning phase, right, in the design phase. So as we mentioned, there are like different approaches. Argonne has this giant climate model, and they can like
generating the future weather file from the supercomputer running like hours. However, there's also like more practical ways. Arab has developed a method, I think called morphing, trying to develop this future weather file through the TMY file. And there's other studies around like using machine learning and integrate uncertainty analysis into the like future weather file generation. Yeah, I'm just trying to say that there are some existing studies from the reading performance analytics community. I would love to connect and then maybe talk about.
Great. Yeah, if you can connect us to other things that have been done in the space, that'd be fantastic.
All right. Ethan, if folks are following up with you, should they contact you over email? Or maybe you're monitoring the chat here, but yes, definitely would love it if folks would respond to this call to action here for EE weather. And Ethan, you can, having written a lot of the code for better or for worse in EE weather, please feel free to use me as a resource as well.
Thanks, Phil.
All right. Any other words on that, Ethan, or anybody who wants to jump in there that didn't get a chance? Excellent. Well, thank you, everybody, for making the time to be here. Definitely thank you to Travis as well for all of that work. And we look forward to continuing this, I believe, in 2 weeks. And somebody please correct me if I'm wrong. Excellent.
Do we intend on doing this during the Christmas holidays? Or are we going to? Yeah, that would be on the 20th. Or do we want to delay until more like the 3rd, maybe?
Be on the lookout for an email. We'll figure that out. I guess offline here, and we'll do an email blast out like we did this time, and so you should have the next date on in your email inbox. Does that sound good?
Just one thing I wanted to talk to Ethan. For the data that you mentioned, that you have some friends that capturing the data. Actually, we want to map the customers within a vicinity. So anonymous data would be possible for that. We don't need the actual location. Some guessing of the location would be great because we're going to map that based on latitude and longitude.
Yeah, there's an interesting question about whether it makes sense to average data across multiple sites or whether it should be actual data, but just blurred location, because you've got cloud cover issues and like local shading issues and things like that. I agree with you. It is possible to anonymize it. The question is like, how difficult is it to anonymize it, and who do we have to convince it's anonymized enough in order to get permission to get it out? So I will start to investigate that and let you all know whether there's at least a glimmer of hope. It's definitely needed. I think this has been a gap for a while that we've struggled with. I mean, it'd be great to bring humidity and wind in, but I think that's like already in the NOAA data. That's not so hard. Irradiance is a beast.
Absolutely. Excellent. All right. Thank you, Ethan. Thank you, Armin. And I believe you guys also have your contact information if you want to chat about it between meetings. So thanks, everybody.
Thanks.
Thanks, y'all.
Thank you, everybody. Appreciate it.
Thanks.